Module 7.1 Introduction to Machine Learning Models. In this module, we learn about an introduction to machine learning, theoretical concept behind machine learning, how to apply machine learning for mechanical engineering applications such as steel fatigue predictions, and so on. In this particular submodule, we learn about fundamental principles behind artificial intelligence, machine learning, and deep learning and how they are related, how to apply machine learning models for solving material design or mechanical engineering applications, how to assess and the capabilities of machine learning tools, and how to use software such as scikit-learn or PyTorch for performing basic simulations and interpret the results. So what is artificial intelligence? AI is a broad field of computer science that concerned with building intelligent machine capable of performing tasks typically require human intelligence. So it basically is a generic term which mimic cognitive functions. Machine learning is a part of artificial intelligence that allows computers to learn without being explicitly programmed and requires subsamples or samples of data set more than 100. And so the models include linear regression, random forest, decision trees, Gaussian processes, and so on, which we'll discuss about. Now, deep learning is a part of machine learning which requires more data, more than usually 500, and they usually entail artificial neural network, CNN, convolutional neural network, graph neural network, and so on. Now, we have to keep in mind that machines do not really understand physics and chemistry or mechanical or material science like we do. They understand or deal with numbers. So we have to take the sophisticated knowledge from mechanical engineering or materials engineering and convert into feature or descriptor in form of numbers that computers can understand. Also, we want to point out that machine learning is not going to replace your experiment or multi-skill modeling tool, conventional multi-skill modeling tool, but it's gonna just help the entire process. So if multi-skill modeling that we learned in previous module help to guide experiment, we are just saying that machine learning can help guide the multi-skill modeling techniques. And if you want to know more about this machine learning and deep learning techniques, you can take a look on this particular review article that we wrote with several authors in this field. And also there's a lot of online resources such as the deeplearningbook.org, and there are many other resources available online that you can easily get familiar with machine learning, deep learning. Now, before we go in the details of machine learning, we should know there are three types of machine learning tools, such as supervised, unsupervised, and reinforcement learning. In supervised learning, we deal with labeled data set where the target output is known, such as predicting the material strength based on composition and structure and processing conditions. So because this is a labeled data set. And some of the common algorithms are linear regression, supporter vector machine, neural network that we'll discuss. Also, supervised machine learning can also be of two types, classification and regression. In classification, we have categorical output, such as cat versus dog, metal versus non-metal, high strength versus low strength, and so on. While in regression, it is with continuous output. So here we cannot just say high strength versus low strength. We actually have to provide some strength, measure of hardness or measure of strength, and so on. So it's Young's modulus or yield stress or something, yield strain or something. So that's like a continuous quantity. So that's a supervised machine learning. However, sometimes we have unlabeled data set. We have a ton of data set and we don't know exactly what to do with it. So what we do with it first is start doing something like clustering or principal component analysis. And that actually helps identify patterns, for example, in manufacturing processes to identify defects without prior knowledge of defect types. Also, there could be reinforcement learning where it involves training a model to make sequence of decisions by rewarding desirable actions. So, for example, optimizing the control system of a robotic arm in real time. So you do some model training, and then you, based on how did it perform, you give it a reward, and then based on this, you keep doing it until a model improves. And it compared to other model, it usually requires less amount of data. And it kind of keep growing itself over time. There are several applications of machine learning in mechanical engineering. For example, material property predictions. such as yield strength, elasticity, and thermal conductivity. So we can use conventional tools such as the density functional theory or molecular dynamics or so on, or perform experiments, or rather we can learn from the data that is already exist and just use that to make a model that can predict the properties for an arbitrary new material. It can also be used for designing or optimizing the mechanical components, such as using genetic algorithm to optimize the shape of an airfoil for maximum lift to drag ratio. So if you want to have genetic algorithm, we basically take a combination of the parent, and then it gives the offspring, and then we mate the offspring, it gives another offspring, and we keep doing that until we get optimum parameters. It can also be used for fault detection, especially if you have a lot of data, such as image data, and you want to diagnose faults in that system, then it's very useful technique to have machine learning. It can also be used for predictive maintenance, such as to utilize machine learning for predictive maintenance by analyzing the historical data to predict future failures, such as using time series analysis to predict the remaining useful life of a machinery. It can be used for process control and automation to develop intelligent control system using reinforcement learning, such as optimizing the welding processes and their parameters in real time to ensure consistent quality. Now let's talk about some of the key principles in machine learning that will be useful for training this such kind of models. First is the data collection. So we require high quality and diverse data for performing machine learning calculation. There's a common saying in machine learning called garbage in, garbage out, which basically if you provide garbage data or not very diverse data or not very high quality data, you will not probably get very high quality model. So what I mean by high quality model is, or high quality data is, it should be very diverse, and it should not have too much noise, outliers, inconsistency, and so on. And we also have to understand what are the features or contributing factors or descriptors that are important in that raw data. As much as possible, we should include domain knowledge that we learned in previous modules, such as combining traditional engineering models as finite element method with machine learning for robust solution. So this is the difference between a data sciences and a mechanical engineering person who knows data science. That's where the difference comes into play. Model selection and development based on what kind of problem you are trying to solve, classification versus regression versus unsupervised task and so on. You might need to choose particular model. We'll discuss about some of that. Also, we want to have a balance between model complexity, that is the number of parameters in a model, and the time to train the model, and how much data we have. So if you have huge amount of data, probably we need more number of parameters. But if you have very small data, maybe we do not need too much complex model. And explainability. As much as possible, we should have interpretable models so that we don't use it as a black box. As we do not generate new samples to test our trained model, what we do is we take a portion of the data set as training, such as 80% as training, and rest 20% as testing. So we train the model on 80% and then test in 20% as if it's the new data and see how does the model perform. And usually these splits are fixed for a particular task, and then based on this we can compare different models using the same training and same test. How does a model perform? But as you can see, this training test split can be a bit biased, or it can be affected by how you split the data. So that's why cross-validation kind of try to tackle this using multiple train test split, using idea called k-fold cross-validation, for example, where you do this train test split like 5 times or 10 times randomly to see how does the model perform. Most of these models have hyperparameters, such as the depth of a neural network or the number of trees in a random forest and so on, that we may need to optimize to get a best model for that particular system. Generalizability and scalability, we have to implement regularization technique. The idea is if you have very complex model and very small amount of data set, or very complicated model, then it will try to fine tune the model parameters just to adjust that particular data set, and it may not perform well for a data set that is not performed. So we need to have some sort of wiggle room for avoid overfitting. Also, as the data set increases, we have to make sure that the model training is scalable for a large amount of data set. We have to understand the evaluation and metrics, such as what kind of evaluation metrics to use. If you're using random forests, such as regression, you might use mean square error, mean absolute error, R square. But if you're using models such as for classification, we can use accuracy, precision, F1 score, and unsupervised clustering kind of technique doesn't really have a metric, for example. And also, as much as possible, we have to validate our model with experimental data or new simulation as possible. We have to keep in mind the ethical and safety considerations so that the data and the model are free from biases. It follows safety and protocols for industry standards and regulations. And we have to continuously update the model in a very systematic, robust way without breaking the entire machinery. And it can be a lifelong learning process. There are different challenges and limitations for machine learning too. We learned about data quality and data quantity. So we need sufficient data and diverse data and high quality data. Else we can get garbage in, garbage out. That's a big problem of machine learning models. So usually it's a common saying that if we have a very diverse data, very high quality data, up to 50% of a problem is already solved. So developing a model is not that in my opinion, very difficult as long as you have very high quality data. Also, we want to have interpretable model so that we don't treat it as a black box model. That's the worst kind of machine learning model. And we also have to keep an eye, how does a model scale? And we have to keep an eye, how does the computational cost scale? That is also very important. And it can be very challenging, especially if you have a huge amount of data and huge amount of parameters, then training them can be very complex. Although it's very natural to incorporate physical laws in machine learning, it's sometimes very difficult to implement this idea. And that's why doing a literature review or knowing the state of the art or developing hybrid models can be very important. As we mentioned, we have to avoid overfitting just so that it doesn't just fit the training data, but also perform well on validation or test data. We always have to validate, verify, and benchmark with the current models to understand the systematic verification of machine learning models to ensure they meet the required accuracy. And of course, we have to meet the ethical and safety considerations.